school, not often people actually manage to spell my name right, so that was a good start. So I'm going to talk about something a little bit different, right? So we've had quite a few talks today about reverse engineering, breaking stuff, looking at the software, looking at mobile phones, extracting secrets and that. I don't know. When I look at security today, I think there are a number of new areas that are a little bit more, a little bit tougher, but also areas that require a different sort of looking at how security is run. And so I'm going to be talking about how do you extract secrets from silicon, in particular, if you master these ways for extracting the secrets from silicon, a new generation of bug hunting. In particular, when I talk about new generation bug hunting, what I'm really talking about is, here is code, microcode, and secrets that have been untouched for 20 plus years. You may have seen a little thing in the news over the last few weeks about vulnerabilities that lie in silicon, right? So where do we sort of start? I think just a little level set. I think when we sort of look at this whole sort of realm of hacking, we need to sort of focus a little bit on what are we trying to protect. And so when it comes to secrets, there's obviously a lot of different aspects to it. But in many ways, from the secrets, we're really trying to protect intellectual property, and that may be things such as cryptographic routines, software algorithms, patent pending techniques, and that. And why are people actually trying to protect these things? This may be to preserve time to market. So, for example, a secret source. They may be trying to control access to a market. So, for example, hardware consumables for gaming platforms. It may be a financial stream. So, for example, streaming data, streaming media, and how do you protect that infringement and copying of those goods. And so before I get on the path of reverse engineering and breaking the silicon part, I think it's important to understand what I mean by reverse engineering. And I think where we start this journey for many, many years has really been about software reverse engineering. And much of the talks today and tomorrow have come from a software engineering and software reverse engineering perspective. And those secrets, the things that we've had to worry about, have traditionally been stored in software. And we've been battling for 30, 40 plus years of how to obfuscate the data and how to move from a to and fro between the hacker, the bad guy, the good guy, and changing techniques. For example, do I obscure the code? I figure out how to de-obscure the code. I now add anti-debugger techniques and so on and so on. And things are sort of advanced, but where we are today with, frankly, the current generation of decompilers and debuggers, there is really no place to secure your secrets entirely in software. Okay, and so where things have sort of moved on, and when I look at where are people keeping their secret source and some of the key elements today, it really has moved into the firmware as well, right? Okay, so if I take my software and as software engineers, I develop my code, I can keep my secrets in that source, and I will try to move some of my secrets to firmware, okay? I'll be able to buy chips, and I'll be able to program these chips and store my secrets. So for example, many of the secure hardware will allow you to use WERN, so write once, read never, which basically means I can put my secret on there. I will never be able to extract that secret, but that secret will be used on the chip itself. And that's all very well. And so from the firmware side, frankly, I think of the last 5 years in particular, many of the tools have now specialized in being able to do firmware extraction and extract secrets from that. So what's happening is that there's a greater emphasis on shifting the secrets to the silicon itself. Okay. There's some advantages by shifting to the silicon and to the chips. First of all, we're talking about the physical barriers. We're moving from those things that you could change from ones and zeros using your software and your regular computer or your laptop, through to a physical medium and the skill sets that are required to break that. But there are also some disadvantages that if I shift my secrets down to the silicon, if someone breaks that silicon, they'll be able to extract that secret, and I'll have no way of replenishing or updating that particular secret. So there are some pros and cons to that. how many people in this room, first of all, class themselves as hackers? Raise your hand if you're a hacker. Actually, very few, okay? How about, how many of you have ever done any hardware hacking? That's a little bit better, I don't know. Obviously, if you should have had to spend some time in the other rooms over there playing around with some of the hardware and some of the hacking side. Hardware hacking is really, it tests a different side of the hacker mentality and the reverse engineering side. And really when we talk about hardware hacking or traditional hardware hacking is, how do I find access to the actual device? I'm going to look for interfaces, I'm going to try to connect to it, I'm going to test those interfaces. And when we're looking at traditional hardware hacking, we're looking at things such as smart card serials, JTAG, USB connectors, and trying to reverse engineer into the protocols and tools. Things get a little more interesting, though, when we move on to the into the IC realm and actually down to the microprocessor. So I'm going to start that sort of journey at a high level. So Intel chip, the 8008 chip. So copyright Intel 1971. So what you see here is effectively a visual image through a microscope of the chip. So you see all the metal layout on what's on there. Interesting thing about this particular chip, it is the ancestor of the x86 chips, so the most common processor that we use today. Back then, 3,000 processors, 0.5 megahertz in speed, and fabrication at its smallest level, 10 micrometer fabrication. When we start looking at reverse engineering from a silicon perspective, there are a number of things that we have to do. So for example, when we're looking at a particular chip here, one of the first things we're looking for are where all the data rails are. Okay, so if you like, what we can see here are a number of colored lines here which actually represent the data lines. And we talk about an 8-bit processor. Every one of these colors represents the actual power line and the data that goes down through individual bytes. Right? Process itself, not particularly interesting, 16 kilobytes of memory. Another aspect of really looking at these chips is, if you like, the diagram of how these chips are supposed to operate. Okay? In many ways, you look at this as a block diagram, and there are a lot of things that are happening on the processor. So when it comes to reverse engineering and understanding the secrets is, how do I go from that metal layer into this block diagram? So if there, for example, if part of this block diagram is a cryptographic routine, I have data that's stored on this particular chip or in memory, and it's encrypted. I have a cryptographic routine, I have a secret, and then I have the data output. Can I figure out a way of bypassing all the cryptographic routines to get to those secrets itself? Things are getting smaller though. So here we were with the 8008 chip, 1971. And here we are with the current generation chips. So for example, this is the Snapdragon 835. It's used in the Samsung Galaxy S8 processors. So it is 10 nanometers. So in 46 years, we have shrunk by 1,000-fold. One thing to bear in mind, though, is that when we talk about these very small fabrications, so 10 nanometers, is that 10 nanometers is obviously very, very small, right? But the chip itself doesn't necessarily mean that everything inside it is at 10 nanometers. 10 nanometers normally is what when we're talking about the size of the chip is this part here of the silicon, and in particular the transistor design. So if you're not quite sure what we're sort of looking at, if you remember back to early stage physics and doing any sort of microelectronics, and you're looking at a transistor, this little part at the top here, this gate cap, represents the base of your NPN transistor. Okay. And so what we've done here is we've taken a slice vertically through a particular chip, and we sort of get the layers of the chip. All right. So moving on to the IC reversing. How was reverse engineering used to be done? Okay, the reverse engineering technique effectively was optical imaging. I take my particular chip, I take lots of photographs of it, I tape them all together and crawl on the floor looking for this. So this happened for debugging. This also happened for looking for security vulnerabilities, faults, and backdoors. We can do a little bit better than that. But where are we today? What sort of happened? What's sort of driving a lot of the silicon reverse engineering today? frankly, when I look at many of the people who have entered this space and enjoying and reverse engineering, you can blame MAME, okay? How many people know much about MAME? I've heard that. Excellent, that's good. How come there's more people knowing about MAME than about reverse engineering and calling themselves hackers here? I don't know. So what we've got here is that as people wanted to recover these old machines, so for example, this is the Sega Virtual Racing from 1992, they had custom code in there. And to be able to preserve these machines, preserve these games, the MAME has allowed us to take those chips, take those processors, extract the code, and then rerun them in emulators. An interesting thing about this is you see this background piece here. So this is one of the chips driving Sega Virtual Racing. What you'll sort of see here, though, is these lines. 1, 2, 3, 4, blah, 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 up to 16 lines, okay? So what we have here is actually the mask ROM for Sega Virtual Racing. Now here's a little trick. If you squint a little bit, you'll see that all the lines that are running up and down this page, some of them have got little dots in there, okay? So those little dots are actually the ones and the zeros of the code there, okay? So you are physically reading the binary code of this game, okay? And if you enjoy doing that, you can actually go to the Capsule blogspot, and they have lots of images of these chips, and you can help them recover code by converting all these back into ones and zeros and back into bytes, okay? But as an introduction, so the interesting thing about this is that if I can get deep enough onto the silicon, I can actually just physically read the data and the secrets that are there. So the reverse engineering techniques really for extracting secrets from silicon haven't really changed an awful lot. So many of the techniques that we've used in the past for conventional reverse engineering of hardware apply to the silicon base. What sort of fascinates me in many ways, hence this sharks with freaking laser beams. Where else in security do we get to play with lasers? We get to play with with acids, fumed nitric acid, and really play at the cutting edge of our chemistry and our electronics side. Things are changing though. As the bad guys get better at reverse engineering the chips, there is a war going on between the hackers, the reverse engineers, and the engineers. So for example, the chips today are designed in multiple ways. So for example, there are a chip is made of different layers of metal, different layers of silicon, different layers of insulators. And some of these insulators may be, can be destroyed through using different types of acids. Some of them may be, can be can be overcome by using different frequencies of light. And there are things such as fuses, so a bit like these sort of meshes running over the top of the chips, for example, to prevent physical access to the chip and extracting the secrets. And there's been a war that's been going on for quite some time in this area. But frankly, the best tool and the best trick that the manufacturers have today is to make things much, much smaller to prevent access to these secrets. On the semiconductor reverse engineering methodology, there are really 5 key steps: decapsulation, delayering, imaging, image analysis, and data extraction, and I'll run through those. So when I look at a particular chip, they're pretty bland. You'll see normally a black piece of plastic with a number of little legs that are sticking out there. So the chip itself is embedded inside that epoxy or that particular plastic, and so decapsulation is about how do I remove this. Lots of different ways depending on the materials, but I won't really sort of step through that. Here we have one particular chip, nice and easy. Frankly, you can play around, but I guess there might be some health warnings there. By dropping a few drops of fuming nitric acid, it destroys the epoxy around this, but leaves the chip around there. Depending on the types of acids, they will expose different types of chips, while leaving, for example, the gold filaments and other parts of the chip itself. Other methods that have available includes things like milling, so using a very fine milling device and gradually removing the layers of the protective measures over the chip, or decapsulation through a laser. Again, playing with lasers to remove down the actual layers themselves. If you get a little bit tired of that, commercially there are tools such as the jet etch, which allow you to effectively hook the chip up there, push it down, and it will do all the work in actually removing all the materials to give you exposure to the chip itself. once you've exposed the chip, you want to do a little bit of cleaning so that you can take nice pictures and nice images on that. That's already about preparing the chip ready for doing the reverse engineering. But so when I talk about delayering, what am I trying to do? So why do I want to delayer a integrated circuit? So if I was to take a normal look at a chip, so for example here we have Apple's A4 microprocessor. From the front, from the back, not an awful lot of help there. It's going to provide me insights into what's going on there. If I take an X-ray, I'll get probably not an awful lot of value out of that X-ray, right? But as I start to extract the layers and actually remove the layers of the chip, I start to get a better idea of actually what's inside the chip itself, right? So for example, here we're looking at the very top layer of the metal layer 8. So what that means here is that the A4 processor has 8 layers of metal into the chip itself. And of course, what I can also do is I can take a slice vertically through the chip and sort of work out all these different layers. This is important for me. By understanding what all the layers are, I can start dialing in how much do I need to remove of a layer to be able to expose the layer below it. But delayering is a difficult task. So for example, what we've got here is that, I talked about multiple different layers. So for example, in this particular chip, we see 5 different layers of metal, and there's layers between there. What we also see are, for example, here some metal areas that cross between layers. Okay, so these are called vias. So this connects one layer to the next layer of the actual chip. It's getting a lot more complicated today. So for example, here is a newer generation of chip, and actually has 3 chips in one stacked on top of each other, connected together, right? And so things are becoming much more complicated, but it's still overcome. So there is an art to delayering, and it's a strange sort of art. Okay, so when you sort of think of these chips, very, very small chips, what I've got to do is I have got to extract micrometers of material per layer, get it evenly, and then take a photograph and then move on to the next layer and move on to the next layer. So when it comes to reverse engineering a chip, normally we're not talking about reverse engineering a single chip. We're looking at a bag of chips and going through many of them because they're getting lost, getting broken, and also it's very delicate work as we remove one layer at a time. And as we move through those particular layers, we can start to reveal the secrets of the integrated circuits. We have a number of tools in our arsenal. Okay, so when it comes to visibility, the 3 big pieces being the optical microscope, so that gives us somewhere between a 500 and 1500 times zoom, a FIB, which is a focused ion beam, which gives us somewhere between 250 to 800,000 times magnification, and then a SIM for a scanning electron microscope, which gives us a 1,000,000 plus magnification. Okay, so I've gone through a chip, I've managed to remove all the protective materials, and then I'm going to go look at each layer of the particular chip and start imaging these things. There are a number of different techniques. So front-side analysis. So this is effectively, if I extract those particular layers, I put them into a SIM, and I start taking an image here, right? If I've got something that's I've zoomed in 1,000,000 times, and the chip itself is maybe 5 millimeters by 5 millimeters, that means I'm going to have something like 300 or 400 images wide by 300 or 400 images deep, and five times the layers of metal, for example. So it becomes a very complex task, a bit like stitching all these sort of images together to build that big map that was laid on the floor originally. So when it comes to reverse engineering chips, this part of the job is the part that sucks the most, absorbs the most amount of time, and was probably where most people in this, who do this type of work lose their hair the most. Right. Another method that's interesting is really the backside analysis. Okay, so this is where I take the chip, I remove some of the substrate, but I can just view the chip, including when it's powered up, from the underside. Interesting part about this is that the underside of the chip will be silicon, right? Because this is where the transistors are. Silicon is transparent to near infrared, right? So by using these particular techniques, I can actually get a layout, an understanding of the chip and how the chip's fabricated and how how the logic of the chip has been designed from just looking at the backside of the chip itself. It's getting a lot more difficult, as more people do this use these type of tools and techniques. One method about this is that you can add dopants to the silicon, which then stop the near infrared from actually working. So again, this good guy hacker back and forth from protecting chips. So as I build up these photographs, I can then start doing sort of image analysis. So for example, here, just using Photoshop, I have all my different photographs of each layer of metal, and I can build these things up there. Again, so I have to layer these things over top of each other, and I can start mapping where all of the actual circuits and routes start going through. Some of the newer techniques in probably the last 5-6 years have focused on the vectorization of this. So what that means is, instead of it being an image, I'm now going to convert it into a vector, a very complex vector, and if I can vectorize it, I can also then start using virtual analysis, so I can virtualize the entire chip. Some of the newest techniques that are coming around really are 3D X-ray microscopes. So this is a brand new type of method. So effectively what we have here is that it's a special type of X-ray that builds up over time and allows you to reconstruct structures at 70 nanometers. Right. And so we start to see, the layout of the chip, but also we get, without having to destroy the chip, we can actually see where all the metal layers connect between each things. So there's a great hope in this type of technology that will actually fundamentally change much of the semiconductor reverse engineering going forward. Another technique, two techniques that have been developed and that are making changes, or that are again sort of changing the way we look at this, are scanning capacitance microscopy, if I can say the word properly, and scanning microwave impedance. So what these things actually do, which is a little bit more interesting, is a hard part of reading silicon has really been some of the memory storage areas. So these new types of techniques actually allow us to physically view flash memory cells. Okay, so as the core storage for most of the microelectronics that we need to worry about, it allows us, for example, through using these two different techniques, we can actually see again, on the chip where the ones and zeros actually are, and we can read the secrets directly from the chips. Another area really is, if I look at the metal layers, I can also look at some of the logic there. So while I might have memory areas and I'm going to store the dynamic memory, or maybe some of the original memory that was put onto the chip, I can also look at some of the secret source routines here. So once you get good at these, you can actually start programming a system to actually do image recognition to identify, for example, the flip-flops and the logic gates that are actually part of this particular system. And folks that do this for quite a bit of the time become very good and become experts at actually spotting where the cryptographic routines are and spotting flaws in the cryptographic routines purely from looking at the pictures. So if all that was really about understanding the chip and being able to access parts of and understand where on a large chip where all the important things are, this is where things start to sort of take off when we get into our hardware reverse engineering, and that's really the data extraction. So as part of that planning for data extraction, what we have to do is we have to look at all those different layers. We have to look at the key structures. We have to start looking at the chip and trying to decide on where all those logic pieces were, the chips, for example, where the encryption pieces were, where the decryption pieces, where the data storage areas are. We also have to look at some of the physical protections. So for example, where there are fuses on the chip. So for example, some protections of chips allow to prevent someone taking out the chip and reverse engineering it. So we'll have fuses on there that will respond to infrared light, for example. Okay. Also, some of the chips will also have, you'll need atmospheric controls because they will destroy themselves very quickly in normal light. So one of the techniques that works very well is using a fib. So again, the focused ion beam, because So the fib we can use to, as a way of imaging a particular chip, but because of what a fib is doing is focused ion beams, if I leave the ion beams charged up enough, powerful enough, it will actually etch holes through the device that I'm looking at. And I have great control, right? So I can, so for example, these are very close-up shots here, and these are the types of holes that I can cut into the actual chip between layers and between individual layers of metal and between the circuits and reach into the chips. Now, once I have those particular holes, I can start putting probes in. Okay, so microprobing is the technique that we use there. And so effectively, this allows us to use those holes and those particular key points in the chip and put individual probes down on there. The trick, though, is that these probes are very, very small. So, for example, here, working on a substrate here for a 8-bit or 16-bit chip, then I have to put down enough probes onto this particular chip. It's pretty scary, though. I think that each one of these probes, when if you think of a very, very fine needle, and yet even on the finest needle you can think of, these needles are still maybe 1,000 times thinner. We've had plenty of times where you lay down all these particular probes during the day, you need to go home, you come back the following morning, and someone drove a truck next to the building, and the shaking of the ground actually caused some of your needles to break, and you have to start all over again. So very sensitive work. What that allows us to do, though, is by putting on the probes, it allows us to start actually doing the probing itself, right? And so we can use, in this case, programmed oscilloscopes and logic analyzers to start looking at the chip and start playing around with the power inputs and extracting data from particular pieces of the chip. That allows us to do things such as glitching. So, for example, let's say I want to, the chip is operating very fast. By using glitching, I can slow down the chip, slow down the memory processors, and look closer at the particular details. I can then bypass, or I can choose to bypass different processes within the chip. Or I can start adding different types of interference to be able to cause strange actions that allow me to extract new data and new secrets from the particular chips themselves. So when it comes to the chips themselves, for example, when I talked a little bit about the MAME and helping MAME recover the chips, the code on mask ROMs. So much of the code that is physically on the chip to begin with is not encrypted. And unlucky for many of the manufacturers of the chips today, those that say that they are encrypting it are actually just XORing the code itself, right? So very easy to extract, very easy to move on. So if I'm able to get that visibility, what else can I do on the chips there? So today, another area of really looking into this area really involves simulation software. Okay, so if I can build up that map of all the layers of the metal there, and I can work out where all the memory areas are, and I can vectorize that, I can now start importing all that data into CAD systems. I can replicate the particular chip, and I can start virtualizing the chip and actually do all of my glitching in memory at a very fast pace. So many of the techniques we've learned over the last decade focused on fuzzing techniques for software can now be applied to the hardware side when we start virtualizing the software of the microprocessors themselves. So what does that really mean? I mean, it's apart from being fun playing with lasers, playing with acids, and extracting that secret sauce, the magic code and things, what does that really mean for us sort of going forward? I'll give you a few examples when it comes through like a consultancy side. Counterfeiting. Why would someone really want to counterfeit chips? So here we have a couple of chips that look very, very similar. They've got exactly the same type of manufacturing stamps on there. They're being called the same type of chip. In this particular case, what happens, the organization that were using these chips in their particular boards were very happy, everything was going all right, until one day the manufacturers put out a firmware update. They rolled out the firmware updates to their hardware, and many of the devices started failing. And what happened was that some of the chips are being counterfeit chips, and they had less memory actually on the chips themselves. And so the firmware had made use of additional code, required additional memory on the chip, thought there was a normal amount of the chip, normal memory on there, and they started to, it started to fail on that side. Why would anyone want to do that sort of counterfeiting? First of all, by counterfeiting, you don't have to pay your sort of licensing costs for these particular chips. For example, you don't need to have additional signed drivers. There's no advertising and marketing, but more importantly, you can reuse existing dies and fabrication technology. Okay, so unfortunately, the market, the gray market for semiconductors, even at the lowest end, chips that are sub $1, is probably more open to counterfeiting today than some of the more specialized chips. So what's sort of happening in that scene as well? What we also see is product teardowns. I thought it was interesting, today there was a good discussion really about reverse engineering the Samsung 3 errors and error problems with that, try to figuring out what the memory was, what was the construction of that. From the other side is that if you work down the teardown side, you actually pull out the microprocessor and you start looking at this. And so, for example, here on the iPhone 8 Plus, we have a system on chip, and we have the size here, and we can start labeling the parts of the chip. So, for example, what's the system on chip? We can see where the main processors are, 2 CPUs, and with the GPUs and that. From an attack perspective, we can then focus on where the memory areas are, and instead of having to reverse engineer the entire chip, dive down to individual pieces. So today there are dozens of sites and dozens of organizations that focus on these teardowns. They're used for understanding what all the processes, what all the versions that are running on there, extraction of data that can be used to work out what is the cost of manufacturing for a device. Another area really is on the IC teardowns. You can actually go a little bit further. So, for example, this particular example is, I might be interested in a particular chip, and I can get all the details about this particular chip already. So, for example, this one here is the IC, or the current generation of integrated circuit for Microsoft's HoloLens, right? And so effectively here, this particular site, they go reverse engineering the actual microprocessor itself, and they will sell you all of the photographs and all the diagrams. So that entire process of reverse engineering, you can go to the sites and not have to do it yourself, just download, pay a little bit of money, and that. And once you have that sort of thing, really you can start focusing on the secrets. So if you don't really want to extract those secrets yourself, there are plenty of organizations who actually specialize in actually extracting those secrets on your behalf. So, for example, what we sort of see here is, if you like, the cost breakdown as a managed service to take your current generation chip, microprocessor, get all the photographs, and actually extract the microcode, the secret source, the secret numbers, and right down here to porting the code from assembler to C so you understand the program as well, right? So there is an entire ecosystem around the reverse engineering of the microprocessors. But it's a bit like that ad, but wait, there's more. So going one step further is not only reverse engineering, taking all the photographs, extracting the microcode. You can now take those photographs, you can take that vectorized image, you could take that Photoshop stack of all the images there. And they will just refabricate the chip for you, right? And you can work with organizations like this where you can modify the code that was on the chip as well. So, for example, changing some of the secrets or adding additional secrets and keys. So, pretty interesting ecosystem that has come to flourish today. What's with that sort of space? What do we really? What's sort of really possible? Okay, so the imaging techniques that we have today, allow us to read the bits at the metal layer. Okay, so that, for example, the mask ROM allows us to get that original code that was etched onto the chip by the chip manufacturers, extract those secret numbers, the secret code, and effectively have full control of the device at that level. It also allows us to read the bits at the silicon level. So if you like, the storage memory, the flash memory, for example, all those things that, as a software engineer, those particular secrets I wanted to store in an impossible to get place, I've moved into the silicon. However, it can now be read either manually or through automated processes. I can read the gate arrays, okay, so I can evaluate the etched algorithms, that secret source for a new cryptographic routine, for example. And I can virtualize everything into if you like, a simulation of the chip, and I can start using many of the techniques that we use for conventional software bug hunting against the chip itself. I've also got a bunch of probing techniques, right? So I can take those code memory dumps and part of an IC, and I can start looking for physical ways of bypassing these technologies. How about an example? Really. And so when I look at one of these things, let's look at attacks against a mass-produced device. This one here is something so interesting that sort of worked, and it was also a bit of a real, frankly, pain in the ass. Is that if you're familiar with the laser printers and laser toners, right? So you may have heard many of the manufacturers saying, our laser printers do not work with non-genuine parts. Make sure you have the genuine laser toner, for example. How many of you realize that, or have sort of thought about how does the printer know that the laser toner is the correct one? The answer to this is that every single toner cartridge has its own microprocessor, has a magic code, and has a magic number. And on the laser printer has a method of reading that and querying that chip and extracting that number and comparing the codes. So for example, so why would someone want to do that? Why would a manufacturer really want to protect their toner cartridges, right? Key things really being on here are, there's a lot of, in the printer markets, the money really comes from over long term from revenues from the actual toner cartridges themselves as opposed to the printer itself. So the longer that a manufacturer can prevent someone using a non-genuine toner or a refresh toner, the longer they can make the maximum return on that investment. Interesting enough, this particular organization that we're working with, their criteria was it should take a minimum of 3 years for someone to reverse engineer the chip, extract the secrets, and to produce and to bring to market a new toner cartridge against this sort of thing. So what does a hacker must do? You must be able to extract the protocols, the functionality, and the algorithms. You need to be able to extract the keys and the sensitive parameters, and you have to figure out how to commercialize the entire attack. The reason why this one was an interesting analysis or sort of work through was these chips are tiny, right? So the chips that are on the printed cartridges are, at least in this particular one that I worked on, are about 0.5 millimeter by 3/4 millimeter in size. Okay, so imagine those photographs where you saw someone using their finger holding it above a little sanding disk, trying to move one layer at a time. You try to get something like that flat and try to remove 7 layers of metal and get the images. Each one of these particular chips looks like you throw them into a bag and it looks like someone's ground some peppercorns, in this type of thing. So much of the techniques and the hardships in actually extracting the secrets has to do with the physical manipulation of the semiconductor itself. I think in this particular one, while the manufacturer were aiming for about 3 years for someone to reverse engineer, I think it took about 5 days, 6 days, if you ignore the amount of time of people losing chips because they got stuck to fingers and things like that. So what were some of the defenses and what sort of things should we really look at? Okay, so when it comes from, hardware and software have to work in symbiosis when it comes to security. Okay, so instead of, the defenses really look about, from a defense perspective, we should be looking at ways that I can revoke and update keys actually on the hardware and the software at the same time. Okay. You can look at more sophisticated crypto algorithms, but frankly, the more advanced crypto is actually uses more energy. But from a reverse engineering perspective, and most of these types of chips that we're looking at today, you can just simply bypass the crypto algorithms themselves by just simply putting your probes in different places and extracting the secrets that way. So software encrypted algorithms in memory that erases the chips in memory, right? So the ability to, again, use that symbiosis where if I feel that this particular chip or range of chips has been hacked, can I now flash that algorithm on those particular chips and reprogram them remotely, so that all that work that went into extracting those secrets and magic numbers no longer actually applies anymore. A lot of work is also going into optical sensors that erase the chips as well. So the ability, if someone takes that chip out, how to destroy the memory on the chip, because of the way that the data would normally be extracted for reverse engineering. I think there's another area, and this is where I do worry an awful lot, really, is about the backdoors. So today, it's down to the manufacturers themselves to decide on how they can and how they will, if they will install backdoors, and that backdoor may be, for example, additional keys. They may depreciate crypto functions. For example, one of the ones that I've seen before is look for a magic number. When the magic number is seen, effectively turn off the random number generator and use a calculation of pi, for example, right? And so these types of backdoors and techniques are appearing in chips and chip manufacturing. More often than not, it's in the counterfeit space. So what happens is that someone will reverse engineer a particular chip. They will extract the microcodes. They will find the secrets in those particular in that particular code. They will then reprogram an FPGA and add their additional routines or add additional certificates, additional keys, and then push that out through the supply chain. One of the hard parts, though, is really hunting for backdoors and chips is really, really difficult. Doing it manually is almost impossible. It's more about being lucky when you actually find these things. So the newer technology is focused on the virtualization of the chip, makes things a little bit easier, but we're still probably half a decade away from that becoming mainstream. So what are the threats that are going forward? Today, if I was to go out and buy a SIM or a FIB, that's about $500,000 per machine, second-hand, right? And if I want to get a focused ion beam system that will handle down to 10 nanometers, it's probably going to cost me about $3 or $4 million. However, if you really want to, you've got two routes. One is you can go to an organization that just focuses on not so much reverse engineering chips, but focuses on debugging and diagnostics, where you can actually rent this equipment for about $300 an hour. Okay, so here we move from $1 million+ for all the necessary equipment down to $300 an hour per lab. Or you go to a university and you do your degree in semiconductors, and most of the devices are actually already there. Most of the technology is already there, right? Other things that worry me really is that the integrated circuit code is immobile. Okay, so today many of the chips and technologies that are out there have been designed to be out there in circulation for many years and sort of go on. So the ability to actually reverse engineer these particular chips and find vulnerabilities means that once you find this particular vulnerability, it is nigh on impossible for the chip manufacturers to fix that vulnerability. And as we look at the IoT space, many of these technologies in the chips, so for example, I was looking at the chips that are used in, what are they called? These are, when you're driving on, you're coming on the road and you'll see sometimes a little cutout circle or a square in the road where there's a sensor that identifies that a vehicle has passed over it. Right, so there's a new generation of these little things that are about this sort of size, maybe twice as deep, which with a little arrow on top, you physically put it inside the road and you cover it up with concrete tar seal and things like that. Every time a car goes over in a direction, it measures how fast the car is moving and what direction roughly, and whether it's stopped. It then broadcasts through an unsecure channel to another system that then helps control the lights, the lighting system, and other feedback for traffic analysis. The problem is that devices from some of the manufacturers have, the chips themselves have vulnerabilities in their, in quotes, secure communications, XOR communications. So now we have a device that's physically installed in hundreds of cities and has a vulnerability that will never be fixed until they physically dig up the roads and put these things back together again, right? What it also means is that, for example, a certain cell phone manufacturer had a proprietary Java engine that they put in physically into the chips inside into their phones. Their reasoning was that they wanted to make that Java as secure as possible, so by putting it onto silicon, no one would ever be able to extract their Java engine, and so no one would be able to find vulnerabilities. Guess what happened? Right? The Java was extracted, multiple vulnerabilities were found that cannot be fixed, and so the answer from the manufacturer was, we have a new phone coming out next year. Okay. So the problem here is really that unpatchable critical vulnerabilities, and they're a black eye for the vendor. And so when I look at the space, I think whether you're a software engineer or a reverse engineer or a hacker, really there is no safe space for securing data today. The techniques that are available to extract from the silicon are interesting, and while there might be disclaimers saying, please do not try this at home, as long as you don't eat Tide Pool for breakfast, take care, you can actually play around with many of these techniques, and just like the hacker areas around here, you will learn an awful lot from this. As a wrap up, hat tips. Two people who are the experts in this area that do this full time, really love this stuff. Krista Tarnowski and Joe Grand, so hat tips to them. Also, if you're interested in sort of learning more about these areas, here are a number of key sites I've used for some of the images in this particular presentation. They'll give you sort of step-throughs and actually give you a few more sort of storylines of, if you like, the good, the bad, the ugly of the technologies that are in this space. But with that, thank you very much. Cheers.